Okay, so hi everyone. Welcome to the final day of this meeting. We're happy to have Russ deliver his second talk on monotonicity for continuous time random walks. Take it away, Russ.
Thank you, Ayal. So thank you all for coming. And I am actually going to start by something a bit unorthodox, which is there is a small, tiny portion I inadvertently omitted from yesterday's talk. And so I just wanted to go over that first. It's too cute to omit. So remember this picture where we had the ideal Voronoi vertices here in purple. And I had this matching to the corresponding Delaunay triangle. So those were the three ideal vertices that are at equal separation from that Voronoi vertex, which makes it a vertex. Now, here's what I forgot to ask you. First of all, these ideal triangles, remember they're geodesics, which means they're Euclidean circular arcs that meet the ideal boundary at right angles. So what are the angles, the three angles of an ideal triangle? First question for you.
The guess was 0, 0, and 0.
Correct, 0, 0, 0, right? Because the two sides meet at right angles to the boundary, so there's zero angle. So therefore, if you recall, it's been a day already, what is the area of an ideal triangle?
Pi?
Pi, right? Because every hyperbolic triangle has area pi minus the sum of the interior angles. All right, so every ideal triangle here has area pi. For each triangle, there's one vertex. So what is the intensity of the vertices? How many vertices are there per unit area?
One over pi.
1 over pi, exactly. So I didn't specify exactly what intensity means, but it's like for the Poisson point process. It's the expected number of vertices per area. Alternatively, because of a theorem of Amos-Naveau and follow up by Naveau and Stein, if you look at growing balls in the hyperbolic plane and count the number of vertices in there divided by the volume of the ball, that will tend almost surely to 1 over pi. Okay, so I thought that was too cute to omit. So back to today's talk. I'll begin. Does anyone recognize where this comes from? Should look familiar to some people, at least the locals.
I don't even know what that is. Monkey ball? Monkey ball? Bucky ball? Joel says bucky ball.
Okay, well, I'll tell you later. That's okay. So I'm going to be talking about continuous time random walk. There are two basic types, constant speed and variable speed. Constant speed leaves every vertex at the same rate. Variable speed leaves it at variable rate. How is it specified? So here I have a little graph with 5 vertices, V1 through V5. So consider any finite graph, and there are these rates, which are non-negative numbers R on the edges. 0 rate will mean the same as the edges not there. So when a random walk is at a vertex, say V2, it has these 3 incident edges, 3, 5, and 6, and it will cross one of those edges at rate equal to the number that's on that edge. What does that mean? It means that there is a exponential random variable, or if you want, a Poisson process. And when the Poisson process rings, in other words, when the exponential variable, the time is up, the first one to ring is the one that it crosses. So that means it leaves at the minimum of these 3 exponential random variables. And if you recall, it's a very simple calculation that the minimum of independent exponential random variables is another exponential random variable with rate equal to the sum of the rates. So therefore, it will leave V2, in this case, at rate 3 plus 5 plus 6, or 14. And that's why it's called variable speed. Okay, any questions on what I mean by variable speed continuous time random walk? That's going to be the topic of the entire talk. Nope. Okay, so what am I going to be talking about briefly? I'm going to be looking at both finite and infinite graphs, usually with some sort of structure, like a Cayley graph. And the question will be, the questions, or many questions, will be how the behavior of the random walk depends on the rates. So if we change the rates, in particular, if we increase the rates of some edges, does that affect the behavior in a monotonic way? So I'm going to give a survey of all sorts of results of this type. I'll tell you about some known results, counterexamples. In most cases, I'll give you a very basic idea of proofs and also mention a number of open questions. So that's the plan. One of the things that will be important is the graph Laplacian. So here's that same graph, and here is the corresponding Laplacian. So this came up before in previous talks. Let me just review what it is. Although this has weights, I don't think we saw weights before. So for an edge that has some rate on it or weight, you put negative that amount. So in this case, it's V1, V2. So it's the indices, the rows and columns are indexed by the vertices. You put negative the rate on those entries. If there's no edge, you put 0. And on the diagonal, you put the sum of the rates, R of X. So therefore, this matrix is symmetric, and all the row sums are 0. So here I've just repeated in light brown what I've said. Now, the infinitesimal generator of the continuous time Markov chain corresponding to this random walk is negative Laplacian. What does this mean? This means that the transition probability, P sub t of xy, meaning if the random walk is at x at some time, and we want to know the probability that it's at y, t units of time later, then what we do is we take this negative Laplacian, multiply by t, and exponentiate, which is just the Maclaurin series, which is convergent. And that gives you another matrix, and we take the xy entry of that matrix. Now, how do we get the xy entry? We take this matrix, multiply by the vector, which is 1 at y and 0 elsewhere, and take the inner product with the vector, which is 1 at x and 0 elsewhere. Okay, we're going to use this. The stationary distribution of this random walk is uniform. This is a nice property of the variable speed. So intuitively, how can you think about it? If you have a uniform mass on all the vertices, each edge is going to interchange a certain amount of mass when it rings in the same direction. So you can think about that as saying the mass is not going to change after a ring of any of the edges. More formally, 1, constant vector 1, is an eigenvector of delta with eigenvalue 0. That's the statement that the row sums are 0. And therefore, it's an eigenvector of e to the minus t lambda, e to the minus t delta, with eigenvalue 1, because e to the minus t times 0 is 1. So that's saying the stationary measure is preserved. Okay, or this uniform measure is preserved, stationary. Okay, now I want to give you a few well-known properties. And again, please interrupt with questions at any time. You'll have to tell Eyal, or Eyal will have to see your hand raised or something like that, or hear your shout. The Laplacian matrix is positive semi-definite, which we will write as delta greater than or equal to 0. So why is this? Each edge, remember, we put in this rate RV, negative it on the endpoints, and it contributes to the sum on the diagonal elements. In other words, there's this 2 by 2 where the 2 by 2 particular rows and columns correspond to which edge it is, multiplied by RV. And this 2 by 2 is easy to see. It is positive semi-definite. So it's a sum of positive semi-definite matrices, and therefore it's positive semi-definite, just by definitions. Very simple. Now, here's a nice corollary. For any vertex x, the return probabilities, P sub t of xx, are monotone decreasing in t, which is also intuitive. The more time you wait, the less likely it is to be at your starting point. So what's the proof? Because delta is positive semi-definite, its eigenvalues, lambda I, are non-negative. So if we take an orthonormal basis of eigenvectors, fi for delta, then we can write P sub t of xx, which was what I gave you this expression before, write these, expand the indicator functions in terms of the eigenfunctions, and you will get this expression here. Sum over all the eigenvalues, or all the vertices, e to the minus t lambda I times the norm squared of fi of x. Well, as t increases, clearly this exponential decreases, and so we get the claimed monotonicity. Are there any questions? Okay, so let's look at an example. Here's a simple graph, 4 vertices, and near the rates 1, 3, and 10. And the corresponding return probabilities from 0 up to time 2 are shown here. Of course, at time 0, they're all 1, because of, if it starts at vertex, it hasn't moved. Now, let me ask you a question. We can see that this dark blue one is decreasing most rapidly at time 0. Why is that?
Did you hear that, Russ?
No, I did not.
Sorry.
Its rate of leaving its own, its rate of leaving is 13, which is the highest in the chain, right?
That's exactly right, right? Remember, it starts at this vertex. It's still going to be at that vertex if it hasn't left. That's what really determines the derivative, is the rate of leaving, which is r of x. Okay? Or negative r of x is the derivative. Okay, good. Now, as I said, this talk is really going to be at monotonicity in the rates rather than in time. Okay, if we change some of these rates, what will that do to return probabilities? Now, one case is simple. Suppose we increase or multiply all rates by the same constant factor. So remember, that just changes the Laplacian by that same factor, which is equivalent to changing time by that same factor. And therefore, we have monotonicity. So this is a general property of most things I'm going to look at. We should first look at monotonicity in time before we ask whether there's monotonicity in the rates. Okay? So let's consider changing just this middle rate, which I'll call rho. And now I have 4 return probabilities to look at, 1 for each vertex. And I can ask, as rho increases from 0 to infinity, will those all or any of those return probabilities be monotonic in rho? Does anyone have a guess? You're allowed to talk among yourselves, by the way. I can't even hear you. Okay, that's okay if you don't have a guess. It's not at all intuitive. In fact, why is it not intuitive? I meant to say this earlier. When one increases rho here, what happens? Well, of course, that means things can only move faster. Of course, it only changes things when the random walk is at the green or the blue vertex, but then it moves faster. But increasing rho also changes the probability of where it goes, right? Makes it more likely to cross that edge. And that makes it kind of complicated. Well, I will tell you, in this example, there are 3 vertices that are monotonic, decreasing in rho, but one of those vertices is not monotonic, decreasing in rho. So given that information, do you have a guess as to which one has this counterintuitive non-monotonicity? That's okay. I don't think it's all intuitive. I forgot to say, we should look at some time, because we're increasing just the rate, so we should just fix some time. And here they are at time 1. 3 is just what I showed you before. It has nothing to do with anything. Rho was increasing. I changed it from 1. Of course, you could go from 0, but from 1 over to 20. And the one that's non-monotonic is this green one here, the second one from the left. It does start out decreasing, but then it goes up increasing and seems to increase forever after that. Notice this axis intersection here is not at 0. It's at a quarter, which was the stationary distribution. But these don't necessarily approach the stationary distribution. There's no reason they would at time 1. Okay? So it's strange. However, suppose that I look at the average of these 4 return probabilities at time 1. Well, that looks monotonic decreasing. And it is. Is this just a coincidence, or is this some general property? Turns out it's a general property. And this was shown by Benjamini and Schramm, published in a paper by 2 others. On every finite graph, if I look at any set of rates, and I look at the average return probability at any particular time, it'll be monotone decreasing in the rates. In other words, if none of the rates go down, some may go up, then the average return probability at that time can only decrease. So that's a nice property. So this was an example of a completely unstructured network, but we, in a sense, introduce some structure by taking an average. You'll understand that more in a bit. So here's a sketch of the proof. Suppose I have 2 rate functions, r and r prime, and r prime is at least r on every edge. Now, what does that mean in terms of the Laplacian? Remember, I was adding those 2 by 2s. Now I'm multiplying them by at least as much as before. So in other words, I add some more 2 by 2s to get the new Laplacian from the old. So it only goes up. That this less than or equal means the right-hand side minus left-hand side is positive semi-definite. So a general property of matrices is that if I look at all the eigenvalues of the former matrix, they can only go up. They're at most the corresponding eigenvalues of the latter for each I separately. That's true. Now, the sum of the return probabilities is the sum of the diagonal elements of e to the minus t delta. We know that this is the trace, and we know that we can get the trace by summing the eigenvalues. Of course, the sum is just a constant times the average. And so now we see that if the eigenvalues go up, the average goes down. Okay? Any questions? Let Eyal know. Now, we are interested in this average, which is the trace, the sum divided by the number of vertices. I'm going to denote this by capital TR, which is a normalized trace. You'll see why in a moment. Suppose I have a vertex transitive network. In other words, there's a graph which is vertex transitive. For any 2 vertices, there's an automorphism of the graph that takes one to the other, and it preserves the rates on the edges. So it preserves adjacency and preserves the rates on the edges. In this case, every vertex looks the same as every other. So all the return probabilities are the same. And so the average is just the return probability for one of them. Oh. But this suggests a question for infinite graphs where averages do not make sense. Suppose I have an infinite graph which is transitive. And now I consider rate functions, which are also transitive. Then I can look at just one vertex. Is this return probability monotone decreasing in the rates? That's the analog of this proposition of Benjamin and Schramm when we've introduced structure. So now you can see what I mean by taking the average was like introducing some structure. Here we have structure on the network itself, where we can't take an average. This is open. Well, there's some things that are known about it, and I want to tell you about that. First, a little bit about Cayley graphs. So here is the Cayley graph of the symmetric group on 4 letters or numbers, 1, 2, 3, 4, generated by these 3 transpositions. You transpose the first 2, the middle 2, or the last 2. And Cayley diagram is a little bit more than a Cayley graph. I said this yesterday, but the vertices are the elements of the group. So these are these permutations, 4 factorial of them. And 2 of them are joined by an edge where you can get from one to the other by multiplying by one of these generators. And in this case, the generators are involutions, which means they're equal to their inverse. So I don't have to orient them. And I just give the color of the edge of the generator that corresponds to that. So here's the Cayley graph of S4. That's a finite graph. And I showed you an infinite graph yesterday. I'll show you more today. So in general, here's the definition. This is going to be more important than it was yesterday. If gamma is a group generated by S, corresponding Cayley graph has vertices gamma and edges x to xs, where x is in gamma and s is in this generating set. Multiply on the right. If we label the edge by s, then we get the Cayley diagram. Now, why are Cayley graphs transitive? Suppose I have a group element gamma and multiply this edge, in other words, both vertices of the edge, by gamma on the left. This is an edge when xs is an edge because of associativity of multiplication in a group. And we can take gamma x to be any vertex y that we like. That's because of the inverses in a group. And so therefore gamma acts transitively on G by left multiplication. Now rate function will be transitive if the rate of this edge is a function of the generator and not of the vertex x. We're only going to consider symmetric rate functions. That's the whole talk. So if S is not on inverse, then this is going to be a requirement. So here's an example of an infinite Cayley diagram, the 3-regular tree, which we talked about yesterday, but this time that's colored with the generators. So there are 3 generators, A, B, and C. They're all involutions. So these are the generators and these are the relations. A squared, B squared, and C squared are all equal to the identity, and there are no other relations. And that's why there are no cycles. Okay, so these are each Z mod 2. This is the free product of Z mod 2 with itself 3 times. And that's what it means. It means it has this presentation. So that's just an example. So I said I was going to tell you what was known about this open question. And before the question was open in this generality, there were some theorems. So the first one is by Brown for finite graphs. It was already follows from that result of Benjamin and Schramm, but this was even earlier. In 2000, if G is any Cayley graph, then these return probabilities are monotone decreasing in the rates among transitive rate functions. So another way of saying that is transitive rate functions are functions now just of the generators. And if the rates go up, then the return probabilities go down for any time. I'll give you a brief idea of the proof. It uses this same idea of trace that we used to prove the result of Benjamin and Schramm, but now this normalized trace. And it applies to what are called equivariant operators, which I won't explain. What does it mean to be a normalized trace? It means that A maps to normalized trace of A is a linear function of A. The trace of A is non-negative when A is positive semi-definite. The trace of the identity is 1. And the crucial property trace of AB is trace of BA. Given this, it turns out you can imitate the same proof as before and get this result. Of course, you have to establish this is a normalized trace. Turns out to be easy. Well, there's another open question that leads to. If we have an infinite Cayley graph, and we have random rate functions, RG, so they're not transitive, but the law of RG is invariant under left group multiplication. And so we get a random return probability and take its expectation. Then do we have monotonicity? In other words, if I have two fields of random rates, where the second one is at least the first, and both fields are invariant, does the expected return probability go down? This is open even today on regular trees. I think it's true, but it's definitely open. Well, there are some things that are known about this as well. Fontes and Mathieu asked this because they also had a theorem. In a special case, if G is amenable, so what does it mean to be amenable? Includes finite. If amenable is like Z to the D, there are arbitrarily large finite sets whose boundary is small compared to the size of the set. In other words, the size of the boundary divided by the size of the set goes to 0 as you take some sequence. There exists some sequence of sets with that property. That's what amenable means. The regular tree is not amenable. Any finite tree that has a boundary size, and a subtree of the 3 regular tree has a boundary which is roughly the same size as the whole finite subtree. So if this is the case, then that property is indeed true. Now, I will tell you how it's proved briefly, but only by telling you about an extension and how it's proved. So this is a theorem I had with David Aldous. If G is a Cayley graph, so we reduce this amenability. We get rid of this amenability requirement, but we replace it by a different requirement. Remember, I said that these rate functions had to have invariant law. The requirement now is that this pair, where I have RG is less than or equal to R prime G, the pair has an invariant law. Then the monotonicity holds. Why is this an extension of the theorem of Fontes and Mathieu? In the amenability case, it turns out you can always prove that such a coupling exists. And briefly, it goes as follows. We start with each individual rate function has an invariant law with this monotonicity property assumed, but that the pair we do not assume has an invariant law. But because of these large sets with small boundary, we can average these rate functions, the law of the rate functions, over this finite set. And that is almost going to be invariant because the boundary is small. And you take a limit or limit point of such averages, and because the rates themselves have invariant law, this averaging doesn't change the marginal rates, but it changes the coupling law. And so you get a limit which is invariant for the coupling. So that's how this is an extension of their theorem. How is it proved? It's again like the theorem of Brown, that for equivariant random operators, I won't say what that means, we have a trace, which is like before, you do this simple thing, and then you take the expectation. Okay, so that is the end of the discussion of this question. So are there any questions about my discussion? Okay. So now let me talk about a different type of monotonicity. So that was monotonicity of return probabilities. How about monotonicity of the distance from the starting point in time, right? We should look at time first. So let d of x be the graph distance between two vertices, and x sub t be our random walk when we've introduced rates on the edges. So now look at the expected distance at time t from the starting point. Intuitively, this should increase in t, right? Because it certainly starts at 0, can only increase. Does it increase in t? Well, unfortunately, no. Here's a nice counterexample by Oded Trump. Consider a cycle on n vertices. Here, n is 19. And drawn with these thicker brown edges, and rate 1 on each edge. Now we're going to add new edges, which are these little thin blue edges, of rate 2 to the minus n. But not between all pairs of vertices, only between pairs of vertices whose cycle distance is at least the square root of n. Okay, so you see there's no new blue edge here, there's no blue edge here. You have to go all the way over to here before you get a blue edge. At least square root 19 in this case, okay? And let n be large. I claim this is going to be a counterexample. And you're going to help me prove it. Let's look at time n to the 1/3. Time is continuous, but we're going to look at time n to the 1/3. I claim that the walker in this new network is likely to be at a certain distance from its starting point. What distance is that?
Joel says n to the 1/6.
Okay, that's a good first thing to say. N to the 1/6. So first of all, the new edges are very unlikely to have been taken at any time because the rate is so small. So it's basically like random walk on a cycle after n to the 1/3 time or steps, roughly, and it'll go roughly distance n to the 1/6 on the cycle. But the question is, what's the distance in this graph between two vertices at distance n to the 1/6 and cycle distance? Well, it's 2. This graph has diameter 2. N to the 1/6 is less than square root of n. You're not going to have a new blue edge there, but you can go to the opposite side and then back. Okay? So at time n to the 1/3, the expected distance is pretty close to 2. How about a time n squared?
It is 1. It is 1. It is 1. One. Oh, you did say it.
1.
Yeah, 1, right? Because it's very likely to be somewhere on the opposite side, and there's going to be a direct edge. What does this mean? Expected distance went down from 2 to 1. Even in this beautiful setting where we have all the structure, it's a Cayley graph with transitive rates. Bad news. Okay? But actually, things aren't quite as bad as it sounds. Mark Braverman observed the following. Now, suppose you have any finite network. This is even better than Cayley graphs with transitive rates. but we start at a uniform vertex and look at the expected distance after time t. Now, this would be monotonicity, which we know doesn't hold. But it holds up to a factor of 2. And this is sharp, this 2 by the preceding example. So that's very nice. I'm not going to tell you about the proof. It's an exercise in my book with a solution in the back if you want to look at it. So this leads to an open question. We can't ask for exact monotonicity, but near monotonicity. If I have any finite graph with 2 rate functions and a uniform vertex, and now instead of changing time, I say fixed time to be 1, okay? But I change the rates. Do I have monotonicity up to some universal constant? And this is open even in the transitive case. I haven't worked on this very hard. I think it'd be really nice to prove. Okay, that's the end of this section, except this is going to be used in the next section. Let's go back to infinite graphs. Here's our tree generated by 3 involutions. Now I want to talk about random walk. First, let's do discrete time, simple random walks. So discrete time steps, we just cross each incident edge with probability 1/3. Now I want to talk about the speed, which is after a long time, there's some distance in the graph or expected distance, and I divide by the time and take a limit. That I'll call the limiting speed or the speed. So for a discrete time simple random walk, what is the speed at which it escapes from the starting point? Anyone? So here's to say the starting point. If the random walk is here, the chance of going further is 2/3. The chance of going closer is 1/3. So the drift in distance is 1/3. So that's the speed. Okay. Now let's go back to continuous time random walk, and let's start with the simplest case. Each edge has rate 1. What is the speed now? Did you raise your finger, Eyal, to give the answer?
Yes.
Right, it's 1. Oh, sorry, it's not. Did you say 1?
Yeah.
It's not 1.
Not 1.
No.
Was it?
I'm sorry. I'm sorry. It's 1.
Yeah.
I was not paying. Why is it 1? It's 3 times 1/3, right? Because it leaves at rate 3 instead of rate 1 like discrete time. Okay. So now let's go back to the case we're interested in, and suppose the rates depend only on the generators. We want to see what happens. So let's suppose the case 2 of the generators have rate 1, but one of them has rate rho. So if rho is 1, we just saw that the speed is 1. What if rho is 0? It's like those edges aren't there. What is the speed in that case? So then if, say, the blue edges are gone, it's just walking on the green and brown edges, right? What's the speed in that case? It's just walking on the integers, right? And we've already used this fact that at time t, the distance is going to be roughly root t. So you divide by distance by time, it'll go to 0. All right? What if rho tends to infinity? What is the speed going to approach? So if the blue edges have rate tending to infinity, that means now every edge is incident to a blue edge. Every vertex is incident to a blue edge because this is a nice Cayley graph, right? Everywhere it is, it's going to cross very, very frequently and then leave one of the other edges. Right? The rate of leaving of one of the other edges doesn't change because it's always incident to those other edges, but the vertex where it's incident to may be different. So it's kind of confusing, right? Not very intuitive. Turns out it approaches 5/3. It'll probably take you 10 minutes or so to actually work that out. Now we have 3 data points in monotonicity and rho. The speed is 0 when rho is 0. Speed is 1 when rho is 1. And the speed is 5/3 when rho is infinity. Well, that's monotone. Is it true in general that it's monotone increasing in rho? Okay. That's the question. Well, here it turns out you can work out the formula for general rho, and this is the speed. Now, this is not obvious whether it's monotone at first sight or even after a few minutes, but it is. But that's not a very good explanation. So is there a good reason that the speed is actually monotone increasing in rho? What would that mean? Well, it would be yes, probably if we could answer the following questions. What if all 3 rates are different? Is the speed increasing in each rate? What if the degree of the tree is larger than 3? What about other Cayley graphs with symmetric rates on the generators? So those are the questions I want to discuss in the remaining few minutes. Special cases is easy if we increase all rates by the same factor, because that's, as we saw, the same as increasing time by that factor. And of course, that increases the speed by that factor. So here is an example. Well, here's an example of something which is very symmetric, and we want to look at the group of symmetries of this. What is this? Well, this came from a reflection group where you take this triangle and reflect it over and over again on all the sides, and this fills out the hyperbolic plane. I took a tiny portion of the University of Texas logo. That's what this is here, and reflected it, and that gave me that. So you see these symmetries. There's 7-fold symmetry, 3-fold symmetry, 2-fold symmetry. Comes from this triangle of angles pi/2, pi/3, and pi/7. And here's the corresponding Cayley graph corresponding to these 3 reflections. And so it has presentation. They're involutions because they're reflections. AB squared is going around this rectangle. BC cubed is going around this hexagon. And CA to the 7th is going around the 14gon. So here's a nice Cayley graph. The white are just the size of the triangles, but the 3 colored edges give the Cayley diagram of this 2, 3, 7 triangle group. Be nice to answer the question, for example, speed of monotonicity speed and the rates for that. So a nice way to answer it, if we could, would be given 2 random walks where one has higher rates than the other, could we couple them so that the more active walk is always at least as far from the initial position as the other? Well, with Grimm-White, we observed that this is impossible, even in the setting of the trees, even when 2 of the rates are 0. That means the walker is just moving back and forth between 2 states. If I have, so the lazy one might move. If I have this coupling, that means the other one has to stay at this further position, the other endpoint than the starting one, for as long as the lazy one does. That's going to be extremely unlikely if the active one is very active. And in fact, if you choose the rates and choose the right time, you can show it's not possible even when all the 3 rates are positive. So that sounds not good. You can't do such a coupling proof. And in fact, in general, there are counterexamples to monotonicity of speed. Here's this counterexample for a finite graph that Oded constructed that I showed you. You take a free product with Z mod 2. So these new edges, which are red here, that don't introduce any new cycles. And then when you increase both rates within the cyclic group, both rates, by some factor, it's like increasing time there. And we know that can decrease the distance. You keep the rates of the same on the new red edges, And when you decrease distance, it turns out that converts to decreasing limiting speed in this infinite graph. However, what about the original question here or example with trees? Turns out that you do have monotonicity in the rates, and you can prove it using coupling. You actually have to use coupling a few times, but of course you have to be careful. You can't get as ideal a coupling as I asked for before. And so I'm just going to pretty much end with this. Give you a very brief idea. In order to have flexibility, it turns out, use a common idea. Instead of using Poisson clocks of rate rho, use Poisson clocks of rate 2 rho, but now when it rings, flip a coin. And if the coin lands heads, you do cross the edge that correspond to this clock, otherwise you don't move. And I will just say step 1 of this coupling proves the following property. Suppose I have 2 adjacent vertices with W closer to the initial position than W prime. Then for any time, our random walk, fixed rates, has the following property. The random walk is more likely to be at W than at W prime. This is a good thing, because what does increasing the rate of the edge between W and W prime do? It makes it more likely to cross that edge when the random walker is at W or W prime, and it happens faster. Now, this is good for increasing speed when the random walk is at W, because then it moves to W prime further away, more likely, and faster. But it's bad when it's at W prime, because then it's more likely to move it closer. But this says that the random walk is more likely to be a W than a W prime. So the good thing is more likely to happen than the bad thing. And that's why this is a good first step in proving what we want to prove. How is this proved? It uses a reflection in this edge, W and W prime. So there's a coupling where if I have 2 random walkers, one at W and one at W prime, then they take the same generators as the other one does, and that's like a reflection random walk, except when they might want to cross that edge, and then you can couple them to be the same. So that's all I'll say about that. And then there's more coupling steps to go. So let me just close by saying that this theorem extends to Cayley graphs of all Coxeter systems. So I was going to show you more, but I've shown you some. These are the infinite ones I showed you. I showed you some finite ones. And Coxeter systems are defined by certain simple properties of the presentation, but the point is that they are abstractions of reflection groups. And the reflection argument, there doesn't need to be really reflections, geometric reflections like I have showed you, but they can be these abstract reflections. And it turns out virtually the same proof. I've only showed you the sketch of the first step, can be used in this general setting. So let me close with this open question, and then I'll stop. Suppose I have 2 random fields of rates on a Coxeter system, with the first being at most a second almost surely. So like before, I've increased the rates, and the law of each field is invariant under left group multiplication. So like I was talking about before, is the expected speed of the first and most that of the second, and this is open even on regular trees. So sorry, I ran out of time. Like yesterday, I'll hang around on Zoom for anyone who wants to talk. And again, repeat my invitation. You can also email me if you want to talk by email or Zoom later. So thanks so much for coming and listening.
Any questions to us?
So you I guess back in the return probability monotonicity, there was so there was some theorem that for amenable things, right, for amenable Cayley graphs, yeah, okay. So we had this, and you said that, and then you have this other theorem that more generally for a Cayley graph, that's yes, this one, okay, and you said that any if you had two of these stationary weights or rates, then like the coupling witnessing this could be upgraded to one that was also stationary, right?
Yeah.
You said this is possible for amenable things. Do we have counterexamples for non-amenable things? Of just like rates, like not to the theorem of just like, you know, weights abstractly that no, they are but we have stochastic domination, but there's no stationary coupling that witnesses this.
Yes, unfortunately, we do. So Odette and I started asking that question back in the mid-90s, and former PhD student of mine, Peter Mester, gave a counterexample on a Cayley graph, which is very close to the regular tree group, just a finite extension. And the rate functions only took values which were 0 and 1. So it's like percolation. Of course, it doesn't really matter, but the point is they had two values. So yes, there are counterexamples where you can have individual rate functions having invariant law, but and monotonicity almost surely for some coupling, but that there is no monotonic invariant coupling.
I see. Is
Yeah.
this also another characterization of amenability, or is
Well, that's an excellent question. We really know very little about these kinds of bad behaviors, even on trees. So if I recall, we did not have a counterexample on trees, but we don't know that it works on trees. And I would expect that there is a counterexample on trees as well. And for a long time, in fact, there's been proposed counterexamples. One of the first ones proposed turns out not to be a counterexample, but you can tweak it a little bit and make the proof that there's a coupling not work. So this is really not understood. It'd be nice to understand it much better. I think it's very interesting.
Thanks.
Okay, so let's thank Russ again for a great talk.
Thank you.